So now I'm going to talk to you about molecular orbital theory. Now, molecular orbitals are very similar to something we've already discussed called atomic orbitals. So remember, when some of our rules when we talked about atomic orbitals still apply when we talk about molecular orbitals. So remember, we have a 1s orbital, a 2s orbital, a 2p orbital, a 3s orbital, 3p, so on. Atomic orbitals refer specifically to orbitals that hang around a single atom. Molecular orbitals, or what we shall refer to for brevity's sake, MOs, refer to orbitals for entire molecules. So the orbitals that form when two atoms bond. So a lot of the same rules apply. For instance, that with molecular orbitals, like atomic orbitals, there's a max of 2 electrons in each molecular orbital. We've learned this earlier in Pauli exclusion principle. It's going to keep coming up again. And also that each of these orbitals have a specific potential energy associated with them. One of the things we know, same thing, that the closer to a nucleus something is, the lower that potential energy will be. Also depending on the shape and whatever else, that's also going to have something to do with potential energy. Another sort of rule that is unique to molecular orbitals is that however many atomic orbitals we start with, we're going to end up with the same number of molecular orbitals. But what we refer to these molecular orbitals as is if we have one atomic orbital, we should make one molecular orbital, although that's not highly likely because you're going to need 2 orbitals to form a bond. So if you have 2 atomic orbitals to start with, you should get 2 molecular orbitals. So since you're always at least contributing 2 atomic orbitals, you're always going to have at least 2 molecular orbitals. So the 2 types of molecular orbitals you'll get is one, the bonding orbital. And then you'll have an anti-bonding orbital. Bonding orbitals are always lower energy. So it's favorable to form a bonding orbital, but anti-bonding orbitals are higher energy because they cause, here are some attractions formed, lower potential energy, anti-bonding orbitals form because there's a lot of electron repulsion going on. So if we look at something simple, move on, and I'm going to give an example. We're going to talk about hydrogen. If we have good old hydrogen is 1s1. 1s1. So let's say if we remember our old orbital energy level diagram, we have 1s is this energy level, maybe 2s is this energy level, 2p is slightly higher than 2s, so on. So let's say if we get another one of those energy diagrams going on the same side in parallel. 2s, 2p. What is going to happen is that these 1s's if they combine to make a molecular orbital or molecular orbitals, so there's one 1s orbital and one 1s orbital being contributed by another hydrogen, so those will combine to form a bonding orbital, and I should actually make sure this is lower than our two s's, but they should be higher than those 1s's, and a non-bonding orbital. So notice how there's a sigma, plain old sigma, and now there's going to be a sigma star. So sigma is our bonding, the sigma star is our anti-bonding. So this, if I take one electron here and one electron here, electrons will then go to the lowest energy level first, and these two can pair up. Well, we've used those two electrons, so there's no reason for them to go into this anti-bonding orbital. So what happens is, so you have a nucleus, and so we see that the greater electron density is concentrated between those two nuclei in this sigma bonding orbital. We also give this a little designation 1s to show that it is formed by the 1s orbitals of hydrogen. Now, the configuration of this then is, sigma, a little 1s subscript, and then a superscript of 2. The same way we would say like 1s2. So this is for hydrogen. So notice how they started with this energy level and contributed electrons, which ended up lower at this energy level. So this is favorable for hydrogen to form this bond because it ends up at a lower potential energy than they started when they were alone. Okay, so if we start from scratch, and let's look at, and I'm just going to start with just my 1s's. Let's now look at helium. So here's this 1s orbital and that 1s orbital, and here's one helium atom and one helium atom. So they both have configuration of 1s2. So 2 electrons in that 1s orbital. If you look at then, so there will be, again, the bonding sigma 1s and the anti-bonding sigma 1s, or sigma star 1s. So I'm going to focus first. So again, we take one electron, and we take one electron, and we put them together. So we filled this energy level, but now we have to put these 2 electrons up into that energy level. This anti-bonding orbital is higher energy than either of these 1s orbitals. So this is unfavorable for helium to do. So this is why helium then decides not to bond. It's just not favorable for it to put electrons into this anti-bonding orbital. So yes, it does start first to share 2 electrons, in this bonding orbital, but then it has to put electrons, because there's already this density of electrons in the center here. You know, it's got to put electrons sort of repelling each other on the outside here, and that's just not favorable, and that just doesn't work too well. So you see they prefer to hang out away from the atom, and so that's sort of farther from both nuclei, farther away from nuclei you get, the higher potential energy. It is possible to form a helium-2 molecule, but only at super high temperatures. Now, if we talk about things like bond order is, it almost comes very close to the number of bonds and a molecule forms. So if we look at hydrogen, if you remember before, that we just had 2 electrons in this bonding orbit, in this one bonding orbital. So bond order always equals 1/2 bonding electrons minus anti-bonding electrons. So if we think about hydrogen, as you recall, had 2 electrons in this bonding orbital. It had no electrons in the anti-bonding orbital. And if we multiply that by 1/2, the bonding order is 1. Well, and hydrogen has that single bond. And experimentally, if they go and they look at, the bond length, then that all agrees. If we look at hydrogen, remember hydrogen does this nastiness here. So again, 1/2. We see that, okay, there are 2 in a bonding orbital, but then there are 2 in an anti-bonding orbital. So 2 minus 2 is 0. 1/2 of 0 is still 0. So there's 0 bond orders. So yeah, those 2 hydrogens just go on their merry way. And they do not want to bond. Or sorry, those 2 heliums, noble gases, decide not to bond. So let's move on. What does this mean in terms of other craziness? What if we start to look at other atoms in